To calculate potential fields, there are two ways. One is the Coulomb approach, of chapter 2. So that means we could calculate the potential field if we integrate this expression right here. But this led to pretty, intense, brutal, barbaric type methods for actually doing this. There's a much better way, which is what I'm going to do in this course, is that we're going to use Gauss's approach. And what's special about Gauss's approach is it's considerably easier. We start with the electric field being defined as the derivative of the electric potential. If we rewrite this, then the potential difference is then the definite integral of E dot dr. Now, why would this be easier? Because if we limit our case, so we should say this assumes you already know the functional form of the electric field. And the electric fields that we've been looking at have been fairly straightforward. And what I mean by that is that we're using Gauss's law. And what this really tells us is that the word Gauss should conjure up only charge distributions of a high degree of symmetry. That means that we limit ourselves to spheres, cylinders, and planes, just like we did with Gauss's law. So there are some iconic problems. So the iconic problems or potential fields that one should know at the level of physics 4b is that one is a charged parallel plate. Which we already looked at that. And the other one here is that it has to be a point charge. We've already looked at that. And the thing that's really different in all of these cases here is that this is the only one where we have a constant E field. This guy is a variable field. So when I go do the integral, I have to integrate this guy, but I'm going to say that that's a pretty nice way of actually doing it. So there's three other iconic ones. So we will use Gauss's method to calculate potentials for, we're going to have solid spheres. So we're going to have spheres. So when I look at spheres, there's a whole bunch of them. We could have solid conductors slash dielectrics. We can have spherical shells. And the other thing that we should look at is concentric shells. So when we're dealing with spheres, we're going to be looking at that. The other thing that we can have here is that we could have cylinders. Cylinders turn out to be much more challenging, as we'll find out. Here, then we just follow the same thing. We can have solid conductors, we can have shells, and we could just keep going on. And then the last thing here is that we want to look at, we can also do infinite planes. So an infinite plane is really the charged parallel plate, but when you use Gauss's method, there's a slight change in that. So the first one I'm going to go after is I'm going to go after a charged solid conductor. So what we're looking at is we want to look at the potential field for a charged solid conductor. So what I'd like to do here is that I want to sketch out this scenario. So let's sketch out this scenario. And so we have to play the same game that we did before. So what I'm going to have is that I'm going to have a conductor that's solid. And if it's charged, that means then all of the charges must be on the surface. None can be inside. And then we'll do the standard things where this is the radius r, it has a charge q. And so then what we have to do here is we have to play that imaginary work game. So here's what I'm going to do. I'm going to take a test charge. I have a positive test charge. And what I'm going to do here is that I am going to move it. How am I going to move it here? I'm going to start at r equals to infinity. And this is my charge little q. And we know that the potential at infinity is 0 because that's the way we defined it. And now what we're going to start to do here is that we're going to start pushing this charge. And it's going to come all the way, let's say, to about right here. And we're going to say that this is our observation P, our point P. So if I look at this, that means I'm moving this guy a distance to R from the solid conductor, and then this guy is R equals to infinity. Now, most of the time, I don't do this, draw this out, but since this is the first time, I would typically just say we're at a point R. So let's write what I just said so that we start off well. So a test charge is pushed. Why does it have to be pushed? Because if this is a positive test charge and this is a test charge right here, then that means here that I'm going against the electric field. So there's going to be repulsion here. So the test charge is pushed externally. So it's pushed from R equal to infinity to the point P located at R. And when I say R, that means it's a distance R from the solid sphere. So then the question that we're going to ask is, what is the potential landscape that the test charge sees? So here we go. So what I said before, we're really asking this question: how much imaginary work is required to move this test charge to point P? And the way we're going to answer this question is that we're going to use Gauss's law, not Gauss's law, Gauss's method to calculate the potential function of this sphere, which is a function of R. So here's what we need to do. So we need the functional form of the electric field of the sphere. Now note, we've already calculated this. You don't have to show me this. We've already calculated this, and this is what we know. So if I have a solid conductor, what am I expecting here? So Gauss's law shows that if I look at the electric field of a solid conductor, outside, let me say inside, it should be 0. Outside, it should be Q over 4 pi epsilon R squared. And this is for R greater than like that. So if I was to plot this thing here, okay, so let me plot this. I'm going to say that I'm going to take a curve like this. And here is going to be only a quarter of the sphere. Now, what we know here is that if I have a solid conductor, we know all of the charges on the outside. So in other words, there's no charge in the inside, it's all on the outside. So in other words, Q inside is equal to 0. So now if I plot my electric field here, and let's say that this is E of R, and this is my R here, what I would expect is that I'm going to have a field that does this. It's going to fall off as the electric field outside is then going to be 4 pi epsilon R squared over Q into Q. And then as soon as I get inside, the field drops instantaneously, almost instantaneously, to 0, and we get this field right in here. So inside here, we expect that the field inside to be 0 because Gauss's law encloses no charge. And so the field looks like this here. So now I'm ready. So one thing, actually, I want to say one thing before we move on. And I think this is an important point for the potential function. You want to look at this point right in here. And I should say that here's an important point. The electric field is piecewise. I think piecewise I could write as one word. Piecewise continuous. But it has no derivative because of the discontinuity. So if I'm looking at this guy, I'm talking about this particular point at the boundary. Now, it turns out that potential functions are always continuous across a boundary. Not true. I mean, it's piecewise continuous, but it's not a smooth transition. In other words, we're seeing here a smooth transition across a boundary. So you got to remember that when you're drawing this. And the other word that's really important here is this word piecewise continuous. That means if I'm integrating the electric field, I have to do a separate integral for the outside and a separate integral for the inside. Because if you look at the electric field, you could see that it's piecewise continuous. So now let's go look at this thing. So now what we want to do here is that we want to calculate potentials and we're going to start with the outside of the sphere. So outside the sphere means that we're looking at the potential greater than or equal to the radius. So let's go and look at that. So again, we want to set up a picture. And you know what? We've already set up a picture right here. And so what I'm going to do is I'm going to draw a quarter, but it's the same scenario right in here. So let's go look at that. So to calculate the potential, think of how much work is required to push a test charge to point P. So if I look at this thing, here's what I'm seeing. So I have my sphere. And it's looking like this. And of course, all of the charge is on the outside. It's a conductor, like we've already mentioned here. So I have plus, 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 plus. And then we know that this distance right here is the radius. So now we start with our test charge. We start way the heck out here, and we're going to bring it all the way right here. So when I look at this guy, I know that there's external work driving this thing in this direction. So we're at r equals to infinity here, and then here we're bringing it to the location of r. So when I look at Gauss's law, I have to integrate the electric field. So if I'm looking at this integral of E dot dr, I have to figure out the direction of the electric field. So because this is a test charge, we see that the electric field is pointing in that direction, but we are clearly moving this guy in that direction. Right away, it tells you, because of the dot product, I'm going to get E of r dr, but now I have a minus sign, and that's due to the dot product. So now I know what that integral is going to do. So now let's set up Gauss's nest for calculating the potential. So now, setting up the potential integrals, I then see that I'm going to take my potential and I'm going to say, I'm looking at starting at r at infinity, and I'm going to take it to somewhere between infinity and big R. So in other words, I'm looking for the potential between these 2 points. Because we need a reference, this is going to be the potential of R greater than big R minus the potential at infinity. So then clearly that has to be 0 as we defined in the past. So then I look at my integral, and it goes E dot dr, and we're coming from infinity and we're going to r, and then we get a minus sign like we talked about before, and then I put in the value for the electric field, which is 4 pi epsilon r squared over q, and then I have to integrate r squared. So when I integrate 1 over r squared, note I'm going to get a minus sign, so then I'm going to get a plus sign over q, and then I'm going to get the integral of 1 over, nope, that's going to be a plus, minus 1 over infinity, which is 0. So in other words, the potential field function is this guy. So I'm going to go delta V of r less than r less than infinity is then going to be 4 pi epsilon r into q minus 0. I mean, this looks like a point charge field. And that's not a surprise, since if it's external to the sphere, the field acts as if all of the charge is in the center of mass of the sphere. In other words, it acts like a point charge at the sphere. So what did we just calculate? What the heck does this mean? So what I'd like to do is I want to draw the potential field. So let's plot out this field. So what I imagine is that I have this. I have a sphere, and I'm only looking at the quarter. And so when I'm looking at this guy, I'm seeing that I have a field like this. And now I'm going to plot V of R. And I know that this is R. And what we said here is that if I plot this function, you can see that this field is going to look like what? Well, this field has to look something like this here. It has to follow 1 over R. So the field on the outside, that guy has to be 4 pi epsilon R divided into Q. You know, I think I'm going to make this in black. So what does that mean? Well, if I look at this curve, we're asking, the question that's being asked here is how high did the charge go up? So I'm looking at my charge. So my test charge is out here. And then I'm going to bring it to this point right here. So when I look at this thing, I'm seeing that this is a positive test charge. I know that this is at R equals to infinity. And then this point here is R. So what am I doing? I am pushing my charge up this incline. And we asked the question, how high did it go? Well, it went this high. And that height right here is that value right there. That's what we just calculated. How high did the charge go up on the potential curve? Now let's go to the inside. So now we're inside the sphere, but we're looking at the potential for R. It's got to be between 0, R, and big R. Now, this is a really important point. It is important to always follow the process of coming from infinity to some point P. You can't just start at the surface because that's not the way we define the potential function. So you got to remember this. Always start at infinity and work your way in. So since the electric field is piecewise continuous, the integral must be split up. between the outside and inside. So let's start sketching a picture for the process. So here, let's sketch a picture of this process. So I want to calculate the potential of the sphere where it's going to be between these 2 points inside the sphere. So I have to do what? I need the potential outside the sphere. And what am I doing? I have to integrate from infinity to r. And then once I get inside, I now have a different electric field and therefore a different potential where I'm now inside like this. So when I start to look at this thing, this really tells me is that I'm doing what? I'm integrating from infinity to r the electric field outside minus the electric field inside. So that's what I mean by piecewise continuous. Now remember, even though we've already written this, I'm going to write it again. This tells me that if I'm looking at the inside, that is 0. If I'm looking at the outside, this is not 0, but 4 pi epsilon r squared cubed. So you could see that we have 2 different electric fields, which means that we have to integrate both of these electric fields. So now let's do this. So I'm going to substitute these E fields into the integral. So I'm going to say delta V of r less than big R is then going to be, we've already calculated the outside. So this should be 4 pi epsilon r over q, where now we're at the surface, right? So this is then, if we look at this term here is the height to the surface. And if you go back up here, you could see that this is the point that I'm talking about, right here. It's the same field. All I'm substituting in is that little r is now big R. And then I come up to here, and then I have to integrate the electric field inside, but that electric field is 0. So clearly, this guy is 0. And what this tells me here is that the potential field inside is big Q divided by 4 pi epsilon big R. This is the potential from infinity to some point inside. So in summary, we have that the potential function of R is equal to 4 pi epsilon R over Q for R greater than or equal to big R. And then inside it goes to 4 pi epsilon big R over Q. And note that this is a constant field, and this is between 0, R, and and big R here. This is our potential function right here. So our job here is that we want to plot and get a sense of this stuff. So the first thing I'm going to do is I'm going to come over here and I'm going to, I think we plotted this, so I'm going to grab this guy. Since we've already plotted it, I don't want to redraw this again, and I'll just modify it. So what I'd like to do is that I want to plot both E of R and V of R. So, you know what? I think I better be careful because I think I drew it right on top of the sphere. Yeah, and I don't want to do that. So I'm going to leave it. I'm going to stick right here. So let's draw this out. So the first thing I'm going to do is that I'm going to draw my quarter circle here. So if I look at my quarter circle, I'm looking at something like this. I know that all the charge is on the surface. And I know that this location right here is R. And I'm going to plot a field that's going to look something like this. So I want to copy this because I'm going to use this again for the potential. So I'm going to say that I'm going to go here, and then over here, I'm going to plot the exact same curve. So the big difference here is that we have an electric field as a function of R. And I thought I had gotten this to 3 squares. So I'm going to pretend that this is right here at 3 squares. And then this guy is also going to be at 3 squares right here. But here, I am plotting the potential V of R. And of course, this is R, this is R. So what we see about the electric field, as we've already talked about, we saw that the electric field comes all the way to the surface and it gets its maximum value right here. So when I'm looking at this thing, we're talking about this is the outside. And as we look at the outside, we see that the electric field outside is equal to 4 pi epsilon r squared into q. So when I look at the potential is a function of 1 over r, not 1 over r squared. So what's going to happen? It's going to fall off slower. R squared falls off faster. So then I would think that I'm going to do something like this. That's looking like this. So right in here, when I'm looking at this, we're talking about this being outside. So what am I really doing here? I'm taking a test charge and I'm bringing it all the way up here and it's climbing. And right here is R. And then once we get inside, then the field abruptly jumps to 0 and we get an electric field of 0. And then we are now inside the conductor here. So if I look at the potential field, we see here is that it's a constant when I get inside. So in other words, I have a field inside that must be continuous at the surface, at least piecewise continuous, and you can see that this is my field on the inside right here. So I see that's the outside. I'm in the inside right here. And you could see that this field right here is going to be a constant field. And right here at the surface, we see that the surface value is also equal to the value inside. And this guy is 4 pi epsilon big R over Q. Whereas out here, I have V outside, which is then equal to a variable big Q over 4 pi epsilon R. So what I want to do is that I'm going to take this guy with me, and I want to interpret what does that mean. So let's go look at that. So there's a lot to unfold. Okay, so let's analyze. It's not the way you spell analyze. The potential landscape. A test charge starts at r equals to infinity and works its way into the solid conductor. So if I look at this thing, here's what I'm seeing. So here's my curve. Now I'm going to get rid of everything. So I'm going to get rid of this. I'm going to get rid of all of these terms. And now I'm just going to intuitively try to figure it out. So now I have a test charge. So what is my test charge? So I'm going to draw it and then I'm going to copy it. This is my test charge. So when I look at this test charge, what am I going to do with this test charge? I am going to start at infinity. Then, just like we did before, I'm going to bring it to some point right here. And then I'm going to continue to bring this all the way to the surface. And then I'm going to make my way into the surface where I'm now moving along this thing. So let's analyze these points. And this is what I see. At V, so at this point, we're going to say that this is R equal to infinity. In other words, V at infinity is 0. And once again, this is our reference. You have to talk about a reference every single time. So now you start to climb the hill. And one of the things that you want to pay attention, maybe I should draw this just a tiny bit better, but I'm not. You're going to see that right here, as I'm climbing, I have a potential that's going to be somewhere between r, little r, and infinity. So I'm outside the shell, and that's how high it has gone. Now, when this charge comes all the way to the edge of the surface, you could see that this height right here is the maximum height that you can get, and this is at E equal to R. And I'm at the max. So even when I'm inside right here, you're seeing that the inside is no different than the maximum value. So now that I have these, let's put into words what I'm seeing here. So let's envision climbing up this potential hill slash landscape. So you're the test charts. So what do I see? At r equals to infinity, the landscape is flat. In other words, we have no slope to the curve. And that's what we mean by v at r equals to infinity equals to 0. There's no slope. So now the next thing that you're going to do here is that as you climb up, there is a gradual increase in slope. So what does that mean? What we do know here is that, so if I'm looking at this and I plot a little curve, I'm seeing something like this. My curve is steep here, and then it flattens down like this. So now I'm going to pick a point. So if I pick a point, let's say that I pick a point right here. So if I look at the slope right here, you could see here is that it's not steep. So in E field language, we say here is that the E field, the magnitude of the E field is equal to the magnitude of the slope. So what I'm seeing here is that if I have a shallow slope, in other words, less steep, then the value that I'm going to get here for the slope here turns out to look something like this, which means that I end up getting a small electric field. In other words, it's a weaker field, E field, I should say, which then means that the electric force repels weakly. But in the potential language, we only changed electric height by a little. Not a lot, so therefore the potential is small. It's not very big. So now, if we continue along the same path, as you continue climbing, the landscape grows steeper. And you know that as you climb up a hill that's steeper, you got to work harder. So the landscape grows steeper and you work harder. In other words, that implies more work. That's what that's really telling you. Now, what happens in the electric field language? Well, I'm going to keep using this curve right here. So in the E field language, or in terms of E fields, what I'm seeing here is that I have this curve right here. So the big difference in this curve here is that now we don't care about that point. The point we care about is somewhere higher. So if I look at this point right here, you can see here that the slope is steeper. So right here, you're seeing a steeper slope. That implies that the potential change, the rate of change, has now become larger. The magnitude of the electric field is larger, so therefore you have a stronger E field, which then tells you is that the electric force repels stronger. So you're feeling it. That's the exact same thing that we said about climbing up. If it's steeper, you're going to feel it harder. So then finally, we get to the surface. So at the surface, no, at the sphere's surface, you have climbed to maximum electrical height. Of Vmax, which is also going to be the height inside the sphere. So, you know what? I should not say inside. We should say surface. So, to get to this point, you've done all the work already. And you might ask the question, why? Because as soon, and you could see the curve here, look at the curve. It's flat at the top. Once you climb all the way, you've climbed the maximum height. So now what you're finding here is that as soon as you go inside the sphere, you're surprised because it's a flat terrain. Completely flat. A flat terrain means zero slope. And if it means zero slope, that means then that you have zero electric field inside. But if you have zero electric field, that means that no electric force can act on you. So if F net is equal to 0, you are in a state of force-free motion. And sometimes this is called equilibrium motion. which means that you are either at rest or moving at constant velocity. So no force is required to keep your motion inside the conductor. So this is kind of a crazy thing. And the reason why it's crazy here is because if I have a sphere, so if we have a sphere here, and this is a conducting sphere, what we are finding is that inside there's no net charge. There's nothing to push back on you. In other words, it's neutral. So if I take a test charge and I put it right here to go across this whole conductor here, requires no work. So that means if I start with some speed v, it's going to continue to move across this thing at the same speed. So we're saying here is that there is no force to change the motion inside of the sphere. So in other words, the electric force inside is zero. So no electrical work can be done on a charge inside a perfect conductor. And that word perfect is important because if you look at electric wires, those are conductors, but they have a small electric field. And the reason why they have a small electric field is because they're not perfect conductors. They're close. So this flat surface inside the conductor is called an equipotential surface.